Alrighty, you're almost to the end of the year. How exciting. We've just a couple chapters left. This one is going to be on magnetism. We finished up with the unit on electricity, chapters 20 through 23 in the textbook. And now we're going to, it might seem like change gears and switch to magnetism, but we'll actually see that there's a lot of connections between what we learn in this chapter and what we've learned about electricity in the past couple of chapters before this. So here we go. First, magnetism is kind of an experimental basis. I don't know exactly how it was discovered, but at some point people noticed that some rocks, typically materials, would have special properties, namely that they would attract to other rocks and stick together. And so they started investigating this, and they found a lot of similarities between these magnetic rocks and electrical charge. So some of the main similarities that they noticed were magnetism is a non-contact force. If you put two magnets next to each other, or magnetic materials next to each other, they'll attract each other or repel each other across a distance. So in that sense, it's very similar to electricity because it acts at long range, just like positive and negative charges attracting or positive and positive repelling. So they didn't want to use positive and negative because they've already used that for electricity. So the two different types of magnetism or of magnet are called north and south poles, which I'm sure you've already heard of. It didn't matter if they called them north and south. These are just kind of names that we've selected, but you'll see in the next slide or two why they relate to geography. And just like electric fields, or electric charges, I mean, like poles repel and opposite poles attract. So north and north repel, north and south attract. And interestingly enough, the north pole of a magnet attracts to Earth's north pole. So that kind of makes sense on why you might name it north. But it has an interesting effect. Since you know that north and south attract, if the north pole of a magnet is attracted to something, then whatever it's attracted to must be a south magnetic pole, which means Earth's north geographical pole, so this is geographic, Earth's geographic north pole is actually a magnetic south pole. So if Earth's north pole was magnetic north, and then the north side of a magnetic compass would repel, not attract. So the main difference between, well, one of the main differences between magnetic forces and magnets versus electric charges is that with electric charges, the positive and the negative can be separated as two distinct objects, and you can isolate just a positive or just a negative. But with magnets, the poles are inseparable. So if you have a magnet, it always has both a north and a south, and even if you cut it in half, you can't separate the north and the south. If you cut a magnet in half, you'll just have two smaller magnets that each both have a north and a south. So we'll kind of zoom in microscopic scale-wise and see why that's the case in a little bit. First, let's look closer at Earth's magnetic field. So inside the Earth's core, you could think of it as a giant bar magnet. That's not realistically what's going on. There's not a giant piece of metal that's, you know, rectangular and oblong with a north and south pole, but it's the net effect of everything else going on that's causing it to have this kind of appearance. So it's believed that Earth's magnetic poles are caused by a molten core and currents traveling round and round, and we'll learn in this chapter and the next that currents moving cause a magnetic field. So that's believed to be the cause. But the effect of that is that the magnetic field comes out the north pole of the magnetic part, which is actually the south pole of Earth's surface. So on the south pole, the magnetic field points essentially straight upward into the sky, which if you were standing here, you'd be upside down. And so you'd be like this. And the magnetic field would point straight up out of the ground. Then it wraps around. So if you're here standing at the equator, or relatively close to it, anywhere, you know, from here to here, it's parallel to the surface. So like, for example, in our classroom, if you hold a compass in your hand, the needle will point parallel to the surface, and it will point roughly north, because all these lines are pointing towards the north side. But you can see that it's off axis a little bit. This is the axis of rotation. So right here is the axis of rotation, but the magnetic pole is off axis a little bit. So magnetic north is not quite geographic north. And you might have heard about that, you know, when you're navigating with compasses, that it's not pointing directly north. The strength of the magnetic field here on Earth's surface, it has a range depending on where you are. It's obviously not perfectly symmetric. Sometimes it's parallel, sometimes it's diving in again, etc. But the average is between 30 and 60 microteslas. So what that tells you is a Tesla, which we'll talk about in a second, is actually a pretty big unit because the magnetic fields that we're going to generate are typically much, much smaller than 1 Tesla. So here's a sim I got from the University of Colorado, where it's a field hockey sim. and it allows you to kind of visualize the magnetic field created by Earth. So here's Earth, and inside of Earth you've got this bar magnet. Again, it's tilted a little bit off the axis of rotation, but it's got a magnetic south here and a magnetic north here, such that on Earth's surface, especially near the equator and a little bit north and south of that, the magnetic field points parallel to the surface, and it points towards the north. So the red arrow is pointing north. But if you actually go all the way to the North Pole, you can see it points straight into the ground. So if you try to use a compass right at the North Pole, it's going to try to point straight into the ground, and you can't figure out which way to go. Likewise, if you go down to the South Pole, the magnetic field is pointed straight up into the sky. It won't point in any of the directions. Now, if you move a little bit this way, then the compass will start to tilt and point you in roughly the northern direction. And it kind of makes sense, because if you're right at the South Pole, which direction is the North Pole? Well, technically, no matter which way you walk, you're going to be going towards the North Pole, because you're at the South Pole and every direction is north. Likewise, if you're at the North Pole, go around. If you're at the North Pole, every direction is south. No matter which way you go, you're eventually, going to be heading south. If you go this way, you're going south. If you go, I lost it. Around this way, you're going south. Or if you come across the front, you're going south, etc., etc. So it's basic, but it shows you kind of an idea of the magnetic field. And if you move the compass around, notice that the compass always points in the direction of the field, and it will line up with these arrows which show you the direction of the magnetic field. So later on in this lecture, you'll see why this magnetic field that goes around Earth is absolutely critical to our safety. It protects us from basically getting murdered every single day. Alright, so notation and units. The magnetic field is typically called the B field and is notated by the symbol B. The units are Tesla, as you saw in the previous slide. 1 Tesla is actually a super, super huge magnetic field. So most fields that are generated in laboratory settings or Earth's magnetic than 1 Tesla. So again, if I say the B field, that is the magnetic field. So now it says we're going to use bar magnets and iron filings to get an idea of how magnetic field lines look. We'll do this in class, but I've got some pictures of what it looks like. If you set a bar magnet underneath a piece of paper and you pour iron filings, the pattern that results will be something like this. So just like you saw in the picture of Earth, the field lines come out of the North Pole. There's no arrows on here, but if you add arrows, they wrap around kind of like this. And an interesting difference between magnetic field lines and electric field lines is, with the magnetic field lines, they're actually continuous loops. So they continue inside and they come around. Again here, this one continues inside and comes around. These continue all the way through and then wrap around. So all magnetic field lines are continuous and they never start or stop. And that correlates to the idea that you can't have an isolated North Pole or an isolated South Pole. So the field lines, there's nowhere for them to start or stop, because there is no such thing as an isolated North Pole to start or stop on, and an isolated South Pole to start or stop on. So if you take a magnet like this and you break it in half, you get 2 magnets. Maybe this is, south and north and south and north. So when you sever it, just, instead of being separated, all of this is south and all of this is north, it breaks apart such that this is south and this is north. Okay. If you put compasses around a magnetic, or in a magnetic field, which is around a bar magnet, you'll notice a pattern in the direction that the compass needles point that perfectly matches the shape of the iron filings, how they follow this trend of going away from the north and into the south, and then, like I said, it wraps around. Through the middle it goes straight through, and then over here it comes this way, maybe it comes out, wraps around. So this is something we can do in class as well. Comes here, wraps around. So what that tells you is, inside the bar magnet itself, the magnetic field lines are pointing this way and oriented this way. And then outside they go out the north and point towards the south. So if you have a whole bunch of little compasses, they'll line up and point in the direction that the magnetic field is pointing at that moment in time. Okay, so how is it that this happens? Some materials, they exhibit magnetic properties and other materials don't. So the actual kind of theory behind why this happens is it has to do with the electrons in each atom and how they spin. So because the electron has spin, which is a property that you might have learned about in chemistry but maybe not, each electron causes a tiny little magnetic field, and there's millions and millions and millions of electrons in any given material. And so all those tiny, tiny, tiny little magnetic fields, they can either be oriented all in the same way, or they can be oriented kind of randomly, and that will affect whether or not they reinforce each other and create a magnetic field, or whether they all kind of cancel each other out. So if there's an overall magnetization based on them all being lined up, then it will create a bar magnet. So here's a slide that will show kind of the two possibilities. So if each of these is a tiny little magnetic area caused by just a small amount of electrons, or even one electron, if they're all lined up like this, you can see that the net effect of all of this is a full-on south to north alignment, which will create a strong magnetic field. On the other hand, if each one is pointing in a completely random direction, some will point left, some will point right, and the net effect of all of those is to kind of cancel each other out. And so here, there's no noticeable overall magnetism effect in a material that has this kind of an array of electrons. So that's all I have for magnetic materials, but of course, you have things like magnets that stick to your fridge, etc., etc. So there are some materials that are permanent magnets that are magnetic all the time, and then there's other materials that can be what it's called a temporary magnet. So a temporary magnet is if you put that object into a magnetic field, then its little magnetic moments, they're called, they can align and create a temporary magnet. But if you remove the external magnetism, they'll go back to being in random alignment. So it's a lot like an induced dipole. If you put the object in an electric field, it'll become a dipole, and it can interact with the other electric objects. But if you take away the external electric field, it'll just be neutral, and the charges will be evenly distributed. So you can have an object which doesn't appear to be magnetic, but if you put it in the presence of a strong magnetic field, all those magnetic domains will align, and then it will temporarily be a magnet. Okay, a second kind of phenomenon besides permanent bar magnets, which are made of materials which carry the property of the electrons lining up and therefore being magnetic, you can also have magnetic effects caused by current carrying wires. So it turns out that if you just set a compass next to a wire, if you have no current going through the wire, the compass won't point in a particular direction. But if you turn on the current and there's current running through the wire, all of a sudden the compass needle will deflect and point in a certain orientation relative to the wire. So it seems like having current go through that wire somehow created a magnetic field that's now causing the compass to change direction. So what that means is if there's current going through a wire, it acts as if it was a magnet creating a magnetic field. So current in a wire creates a magnetic field. That's a really important result, and it actually goes back and explains how bar magnets work. The reason why each of those electrons causes a small little tiny magnetic field that can then add up and reinforce is because the electron themselves are flying around. So it's a moving charge, which is a current. So it's a microscopic current that actually gives rise to permanent bar magnets. Okay, so if you have current going through a long straight wire, I put an asterisk here to kind of explain what I mean by long straight wire. It just means that the wire is much, much longer than where you're looking nearest. So if you're looking within a distance of, say, 10 centimeters of the wire should be maybe 100 centimeters long or longer, so like a 10-to-1 ratio. If you have a 1 meter long piece of wire and you're looking 10 meters away from it, obviously it's not going to have the same property because you're much farther away than the size of the wire. But close to the wire relative to how long it is, this effect will be true. So the magnetic field actually forms concentric circles that radiate around the wire. And so there's two ways that you can go. You can go clockwise or counterclockwise. And so the way that you can remember it is called the right-hand rule, which is going to be explained on the next slide. And the strength of this field, the closer you are to the wire, the stronger it is. As you move farther away, it gets weaker. So the formula for the magnetic field around a current-carrying wire is mu naught, which is a constant, times I, which is the current in the wire. So the stronger the current is, the stronger the magnetic field, directly proportional. Double the current, double the magnetic field, divided by 2 pi r. Okay, so 2 pi is constant also, and r is the distance away from the center of the wire out to where you're looking. So for example, if I want to know the magnetic field strength right here, my r value would be that far. If I want to know the magnetic field strength right here, my r value would just be that much. So the closer you are, the stronger the magnetic field, and the more current there is running through the wire, the stronger the magnetic field. This constant, mu naught, is a constant of nature, and its value is given by 4 pi times 10 to the negative 7th Tesla meters per amp. So the units work out nicely because you've got amps in the numerator here from the current, and amps in the denominator here that will cancel out. You've got meters in the denominator because of this radius, and meters in the numerator that will cancel out. So meters and amps will cancel with this R and this I, leaving you with Teslas, which is the proper unit for magnetic field. Notice that the constant is really small. It's 10 to the negative 7th. And so, if you're looking at a current of 1 amp and a radius of 1 meter, your actual magnetic field is going to be super, super tiny, like 1/1,000,000th of a Tesla. So as I said before, typical magnetic fields are actually much smaller than 1 Tesla. So let's zoom in on the direction and get a little more information about that. The way that you do this is called the right-hand rule. RHR stands for right-hand rule. To find the magnetic field, point your thumb in the direction that the current is going. So if the current is going, say, upwards, I point my pencil upwards, you put your thumb in the same direction the current's going, and then if your fingers curl around, whatever direction they curl around is the direction that the magnetic field is going. So if I point this at you, my thumb would be coming at you, my fingers would curl around this way, which I guess for you would be, let me think about it, counterclockwise. So the way it's coming at you right now, I think, is going to be counterclockwise. If the current is going away from you and the fingers go this way, for you that would be, my fingers would be going around this way, that would be clockwise. So whether the current is coming towards you or away from you, or if it's up or down or left or right, just point your thumb in the direction of the current and then wrap your fingers around. Whichever way your fingers wrap around, that's the direction of the magnetic field. So for example, over here on this side, the fingers are pointing away from you, but if I continue wrapping around, then on this side, they're coming at you. So the direction of the magnetic field is constantly changing as you map yourself in a circle around. So if you put a little compass right here, the arrow would point this way. If you put that same compass right here, the arrow would point this way. Obviously, if you put it right here, the arrow would point this way, etc. So it's pointing in a concentric circle around that. So the compass will enable you to find the direction of the current as well. If you put the compass down around it, you can tell by thinking of this thing backwards whether the current was going up or down in a wire. Okay, let's take a couple sample problems and see if we can make any sense of this. For the various configurations drawn on the board, find the direction of the current or the magnetic field. So I'll just make up a couple here. If the current is going that way, find the direction of the magnetic field. Okay, so you need to point your thumb in the direction of the current. So your thumb is going this way, and your fingers are going to wrap around behind the wire and then down in front. So behind the wire, you're going up, and then in front of the wire, you're going down. It's kind of hard to draw 3D, but that's about as best I can do. Another option is look at it like this. What if the current is going into the page? So this is the current. The symbol for going into the page away from you, as if you were looking at the wire end on and the current is going away from you, is an X. And the symbol for this, I'll write this, into the page. And if it's coming at you out of the page, you put a little dot with a circle around it for the current. This is out of the page. And the way to remember this is it's like an arrow. If an arrow is going away from you, you're going to see the fletching of the feathers. If the arrow is coming at your face, pointed straight at you, then you're going to see the dot, which is the tip of the arrow. So out of the page and into the page are either X's or dots. And you're going to need to use this a lot because since everything is all perpendicular, you can have up and down and left and right, but you're also going to need into the page and out of the page coming at you. So if the current is going into the page, point your thumb in the direction of the current and then wrap your fingers around. So my thumb would be going that way. My fingers will wrap around like this. So the current will be going clockwise. Likewise on this one, if the current is coming at me out of the page, my fingers are going to wrap around the other way. And there will be multiple concentric circles, and the strength of the field as you get farther away will get weaker and weaker. Okay, for example, what distance away from a long wire with 2.25 amp current would the magnetic field be 50 milliteslas? So we've got our formula. Magnetic field caused by a wire is mu naught I over 2 pi r. And the question is, what distance away? So we're solving for r. So multiply both sides by r, divide both sides by b. So we get that the radius is mu naught I over 2 pi b. we can plug in our values. Mu naught is 4 pi times 10 to the negative 7th. Current was 0.25. Okay, 2 pi here. And magnetic field 50 times 10 to the negative 3. Okay, so we can cancel out the pi and the pi. 4 divided by 2 is 2. 2 times 0.25 is 0.5. So this is 0.5. If I move this decimal 2 digits this way, I can also make this 0.5. And if I move the decimal place 2 points this way, that'll be 0.5 times 10 to the negative 1. And this was 0.5 times 10 to the negative 7. So my final answer would be 1 times 10 to the negative 6 Teslas. So 1 micro Tesla. Okay, so that's a pretty small field, even though we're relatively... Oh, wow, I'm not paying very close attention at all. I apologize. I'm finding the radius. So it should be meters, not Teslas. It's me not paying attention to my units. So 1 times 10 to the negative 6 meters is actually really, really close. So let's see if this makes sense. We want to use only 0.25 amps, which is a low current, and we want to have a 50 millitesla magnetic field, which is actually pretty strong. Remember, the Earth's magnetic field was in the microtesla range, so the millitesla range is about 1,000 times stronger. So we're actually going to have to get really, really close to that wire to have such a strong field. Okay, what happens if you have a loop of wire? So you take a long straight wire with the current in it, and it's got magnetic field that's going around it in concentric circles that are loops. If you take this end and this end and kind of wrap them around, you're still going to have these concentric loops going around. And what happens is that if you kind of look at this from the side, slice it and look at it from the side, all the current, like these are the loops going around, individual loops. And the net effect is that it's always going the same direction inside, and these wrap around so that on the outside it's always going the other way. So it's kind of cool because inside the center of the ring, the magnetic field is always pointing either up or down depending on the direction of the current, and then outside it's always pointing the opposite direction. So inside the center of the loop is kind of a little sacred area where you have all the magnetic field pointing in the same direction. And so that's to our advantage. Using the same right-hand rule, you can figure out whether the inside points up or down. The reason it's to our advantage is because we can take a whole bunch of these loops of wire and we can stack them on top of each other like this, so that each one creates a magnetic field, say up. This one makes one that's up. This one that makes one that's up. This one makes one that's up. I'll just draw it one more. Up, up, up. So each one has, say, a magnetic field pointing up through the center of it. If you put a whole bunch of them stacked on top of each other, then the magnetic field is going to keep pointing up through all of them. And so if you take that thing and tilt on its side, what you get is something like this, where inside the magnetic field is all pointing the same direction. And if you make this stack of rings long enough, it'll make a uniform field inside. So having a uniform field is important for a lot of things, because if the values are constant, it allows you to easily calculate forces and accelerations on particles. So just like for an electric field, we used a capacitor to get a uniform field. For a uniform magnetic field, we use a coil or a whole bunch of concentric rings, and it's got a special name called a solenoid. So a solenoid is a really common device in circuits and magnetism and electrical stuff because it creates a uniform magnetic field in the center. And then outside, the magnetic field lines then bend and wrap back around. So it's a lot like a bar magnet. Let me go back to actually the picture of a bar magnet. It's way back here, where it's a uniform field pointing one way inside, and then outside it wraps around and points the other way. So a solenoid, or a coil of wire, acts as though it's a bar magnet. The benefit, though, is that with a bar magnet, it's solid inside. You can't put anything in there. Whereas with a solenoid, it's hollow inside, and you can actually put charges and particles in there, and you can do experiments with them. Okay, Okay, so again, to find the direction of the current, just use the right-hand rule, and remember that the field inside is uniform. And uniform means constant magnitude and direction. So the force on it will be constant magnitude and direction as well. Constant magnitude and direction. So here's the second example of a magnetic field that's generated, this one by an electromagnet. So if you have a battery powering a coil, the current is going to be wrapping around and around and around, which creates a magnetic field inside that's uniform strength and direction. And you can see that if I decrease the number of loops to only one loop, then the magnetic field kind of bends around rapidly. So the area where it's uniform is very small, but as I increase the number of loops, up to, I guess, 4 as high I can go, then inside, the amount that you have a uniform field, the physical space that uniform field extends through, is much larger. So the longer the coil you have, the more space you have. Then the charges are going out the negative side of the battery, which are electrons, and wrapping around the coil. So pretty basic, but again, it gives you an idea of how an electromagnet works. All right, so this idea that you can wrap a coil of wire and create a magnetic field inside gives rise to what's called an electromagnet. So if we take the idea of a solenoid, which is the coil of wire, and then you run a current through that, by turning the current on and off, you can turn the magnetic effects on and off. And so it allows you to basically have a magnet that you can selectively turn on and off. And because magnets enable things to move, you can then turn the motion on and off by turning the current on and off. So an example of something like this would be the locking mechanism in, say, a car door. When you hit the button, it can turn a circuit on and run current through something, and then say here's the bolt and here's the lock. When you turn the current on, the lock mechanism can be made of some magnetic material. The magnetic field that's created will push that forward and embed it into some kind of, hole, and then the door is going to be locked. And then if you press the other button to unlock it, the current goes in the opposite direction, which puts a force in the opposite direction, which pulls it out and then enables you to open the door. So electromagnetics can be used to lock and unlock things, and a whole wide range of other applications. Basically, anytime you need to move something forward or backward, to turn a switch on and off, it can be used to open and close a switch, etc., etc. So as long as you have a magnetic material inside, when you turn this current on, that object will then try to move forward or backward. So you can also make the magnetic field even stronger by putting a permanent magnetic material inside. So when you turn the current on, not only do you have the magnetic field created by the current itself, but it also causes that material that's inside of it to have all of its domains align, which causes even more of a stronger magnetic field. So you just have a stronger effect overall. And we're going to make an electromagnet in class, and you can use it to pick up metal objects just by turning the current on and off. It's kind of cool. All right. Maybe now is a good time to take a break, actually. So we've covered the idea of permanent magnets, which have all of their little domains and electrons lined up to make an overall magnetic effect in a material. Then we've talked about electromagnets and the idea that current through a wire creates a magnetic field. And if you coil that wire into a solenoid or a coil, it'll create a uniform magnetic field inside. And then one application of that would be an electromagnet. So take a break, and then we'll continue on in a little bit. All right, welcome back from your break. So the next section is going to be on how magnetic forces affect particles. So it turns out, very, very interesting, that since currents act like magnets, we know that there must be a force between the current and the magnetic field. So somehow a current creates a magnetic field. But if you think about it, all a current really is a whole bunch of individual moving particles. So somehow there's an interaction between those individual moving charges and the magnetic field. And it's a very interesting result, but it turns out that a magnetic field will exert a force on any charge that's moving. So if the charge is just sitting still, there will be no magnetic force on it, but as soon as that charge starts moving, then there's going to be a magnetic force. And it's a kind of crazy, maybe new thing that is very different than what you've learned in the past. Normally the force is in the same direction as, say, the gravitational field. Like the force of gravity points in the same direction as the gravitational field. The electric force points in the same direction as the electric field. But with a magnetic force, it actually points perpendicular to both the field and the direction that the charge is moving. So suppose you have a magnetic field. Say these x's all represent going into the page, and your particle is moving upward. Then you need to make what's called a right-hand rule triad, which means you have 3 fingers all perpendicular to each other. So these are perpendicular, and these are perpendicular. Last one perpendicular this way. One finger, say your thumb, can represent the velocity of the particle, as here. Your pointer finger can represent the magnetic field, so those two are perpendicular. And then the one that's perpendicular to both of those would be this finger sticking out here. That's the direction of the force. So which way is the charge moving? Which way is the magnetic field? The force is perpendicular to both of those. And you have to make sure you're using your right hand for positive charges. Negative charges, you can either use your left hand or you can do the opposite of your right hand. But a lot of times you'll be writing with your right hand and you'll pull out your left hand and it will give you the wrong answer. So the strength of the force is proportional to the charge, the speed, the magnetic field, and the sine of the angle. So sine of the angle, sine of 90 degrees equals 1. So the force is maximized when you're having a 90-degree angle between the magnetic field, which is in this case is going into the page, and the velocity. So it's the velocity and the magnetic field that's the angle between these that you're measuring for theta. So you ask yourself, which way is the particle going? Which way is the magnetic field? What's the angle between them? A lot of times, especially in the problems in the book, these two are going to be perpendicular. So it'll be sine of 90, and this part here will just be 1. Then the force is perpendicular. And this is something that's kind of easier to explain in person when you can actually, I can help you orient your hand in the same direction. So we'll do a lot of this in class. But it's called the right-hand rule for forces. And it's a velocity, magnetic field, force triad. So velocity, magnetic field, and force. So if a magnetic field causes a force on an individual charge that's moving, and a current is just a bunch of individual charges all moving in the same direction, then it makes sense that a magnetic field would cause a force on an entire wire that's full of charges. So that's pretty cool. So the force on an entire wire is going to be I times L times B. So I is the current in the wire. That's basically the amount of charge going through it. L is the length of the wire. The longer the wire is, the more charges are moving through it, the bigger the force is going to be. And lastly, the strength of the magnetic field. So this formula, ILB sine theta, is really just a derivative of QVB sine theta. So Q is an individual charge with an individual speed with a magnetic field. And then I times L is the total amount of charge moving through some wire. So current and length has to do with how fast it's moving and how many charges there are moving. And then they both have the B sine theta. So if you've got a current carrying wire, say with a current going this way, and you've got a magnetic field, say coming out of the page, I'll just draw a couple. Say your magnetic field is coming out of the page. You've got your triad, magnetic field, velocity of the particles, magnetic field, and force. Well, the velocity of the particles is in the direction of the current. So for me, I think the orientation is flipped for you guys. Anyway, let me see if I can do this right. Well, I'll just do it based on my orientation. Looking at my screen, I've got the current that way, the magnetic field out of the page, which is this way, so the force is down. So I've got a force down. I think with the flipped screen, it might be different for you. But if you use the right-hand rule in this triad, you should get the same force if the force is going down. And so what that means is, if you have this wire in this magnetic field, literally the entire wire is going to have a downward force pushing on it. And I can do this in class. It's ridiculously cool. You've got a wire inside a magnet, and when you turn the current on, the whole wire just gets pushed down. So it's pretty cool. And you can run multiple wires to get a stronger current and have a bigger physical effect of moving these things back and forth. So just like with the previous formula, the angle is measured in between the current and the magnetic field. So whichever way the current is going and whichever way the magnetic field is going, in this case they're perpendicular, so it'd be a 90-degree angle. Alright, let's do a sample problem. You shoot a proton with a speed of 2,000 meters per second into a magnetic field with a certain strength, 50 milliteslas, that's perpendicular to the path. What will the acceleration of the proton be at the instant it enters the field? What will the direction of this acceleration be based on your drawing? So we need to draw a little picture. you shoot a proton into a magnetic field. So let's make the magnetic field into the page. So there's our B field. And then let's make the charge get shot in from the side. And then let's use our right-hand rule. So the velocity for me is going that way, the magnetic field is going into the page, so the force is going to be up. So for me, the force on this particle is going to be up, which is what that's gonna do is it's gonna take the path of this proton and it's gonna kind of bend it upward. Let me just go forward one. After this, I'll go back one. So the force is gonna start off going up. At the instant it enters the field, we've got a formula F equals QV B sine theta. What is the acceleration of the proton? Well, if this is the only force acting on it, then we know that F equals ma. So the acceleration is the force divided by the mass. So the acceleration is going to be this value divided by the mass of a proton. So the acceleration is going to be the charge on a proton, 1.6 times 10 to the negative 19th, times the velocity, which is 2,000, times the magnetic field, which is 50 milliteslas, which is 50 times 10 to the negative third, divided by the mass of a proton, which is 1.67 times 10 to the negative 27th kilograms. Okay, I don't have a calculator with me, but if you type all that stuff into your calculator, you'll get the answer, and it's going to be a really, really, really big acceleration. So that means the charge is going to have a huge acceleration, which is going to make it bend around, and it will basically go around in a very tight circle. Let me go back one picture and kind of show why this is going to go in a circle. If you look at this one here, at this particular position, if the velocity is up and the magnetic field is into the page, if you use your right-hand rule triad, velocity up, magnetic field into the page, force is to the right, which for me is to the right. Again, you'll have to do it yourself on your screen. It might be backwards from what you see on my hand. As the particle bends around, though, maybe now it's up here. Now its velocity is this way. So if you do the right-hand rule with its velocity this way, magnetic field in the page, now the force is downward, which is going to, again, bend it around this way. So when it gets to here, its velocity is this way. So velocity this way, magnetic field this way, force into the page. Or sorry, force, I can't talk. Velocity down, magnetic field into the page, force to the right. And likewise here, if it's moving velocity this way, force is this way. So you can see that at every moment, the force is pointing inward towards the center of the circle. And we learned a long time ago in first semester that when you have a force that's always pointing towards the center, that causes circular motion. So a charged particle put into or shot into a magnetic field will actually go around in a circle forever. So it can get trapped, so to speak, in that field and just go around continuously in a circle. Okay, so let's do a quick recap of what we've talked about up to this point. The current in a wire causes its own magnetic field. So if you have current going through a wire, it will create a concentric circles of magnetic field around it. If you have a wire with current that's resting in an external magnetic field, there will be a force on it. So current in a wire creates magnetic field, but if you have a magnetic field from something else, it'll put a force on a current in a wire. And individual charges, if you shoot them through magnetic fields, they'll experience a force and have a bent or circular path. Okay. What magnetic field strength and direction will be able to levitate a 2-gram wire with a current of 1.5 amps, as shown below. So if you have a wire, you're going to have a force of gravity pulling down on it, and the force of gravity overall, it's going to act in the center of the wire with a net force of mg. So we're going to need a magnetic force, F sub b, because b is magnetic. We're going to need a force upward to counterbalance this force of gravity. So we know that there's a formula for the force on a wire, F equals IL b sine theta. So you have a couple of questions. One is, what's the strength needed? The other is, what is the direction that's needed? So this force should be equal to this force. So we can set this equal to mg, and we can solve for the magnetic field. We divide both sides by IL and sine theta. We can make theta 90 degrees because we get to choose the direction of the magnetic field. So sine theta, we'll choose this to be 90 degrees, which means this is 1. So magnetic field is going to be mg over IL. Mass is 2 grams, so 0.002 kilograms. Gravity is 9.8. Divided by the current, 1.5 amps. And the length of the wire, I guess I didn't show the length of the wire. So it's impossible to know, huh? Because we don't know how much of it is in the magnetic field. That's very strange. So let's suppose that the length of the wire is 1 meter. So it's going to be a very, very thin wire because it's only 2 grams, so 1 meter, hypothetically. I apologize, I left that out. So if we type all this stuff into our calculator, I don't know what we get. So 0.002 times 9.8 divided by 1.5 times 1, you'll get some answer. I apologize, I'm not having a calculator handy. But whatever you get, that's the magnetic field. It's going to be a pretty small, well, it's going to be less than a Tesla for sure, but it's still going to be pretty large magnetic field on a relative scale, because remember, 1 Tesla is really big. Milliteslas are kind of medium size, and microtesla is pretty small. But I'm more concerned at this point with helping you get the direction. So we have to use the right-hand rule. We know that we want the force to be up, and we know that the current is going towards the right. So our thumb is the current, we put that towards the right. We know that the middle finger, which is the force, needs to end up pointing upward. So I've got my thumb pointing towards the left, my middle finger has to be pointing upward, which means the magnetic field must be pointing at us, which is coming out of the page. So we would need a magnetic field out of the page. If this directionality of the right-hand rule is confusing, especially because of the video and everything's being, I think, reversed, I'm more than happy to explain it again in detail in class. So you need a magnetic field out of the page to put an upward force on this wire. And if you type in these numbers to your calculator, that will tell you the strength in Teslas of the magnetic field that's needed based on the current going through this wire. So you can levitate things using magnetism and currents. Alright, now for something really fun and cool. How does Earth's magnetic field protect us? Well, coming off of the sun, you've got a ton and ton and ton of charged particles that are getting thrown out from the sun. All these charged particles that are headed towards Earth would hit us if they weren't deflected or diverted away. But because the magnetic field comes out of the south and goes into the north, it comes out of the south and goes into the north, because it's out of the magnetic north into magnetic south, you've got magnetic field lines that are pointing upward right here. So when a charged particle, say some positively charged particle, comes shooting at us, you can use this right-hand rule and you can say, okay, the velocity is this way, the magnetic field is up, so the force is pointing towards me. So what's going to happen is this particle is going to kind of divert around. It actually won't curl back, it'll just keep curling this way. And if it was a negative charge, it would divert around that way. And when I show this one, I kind of mean laterally on the same plane, it gets bent this way, or like, so if here's Earth and the charge is coming at us, it doesn't go up or down. It goes around this way, or it goes around this way. But still, it's really cool, and you can calculate based on the strength of the Earth's magnetic field and the speed of these particles coming off the sun exactly what amount of bend they're going to have, and see if they're going to miss the Earth or hit the Earth. And if all these charged particles didn't bend around the Earth, they would all hit us, and that would be an extremely large amount of dangerous radiation, and there would probably be a lot of mutations or dead people, lining the corridors. So that's I think another part of the fear that came with that 2012 fiasco about Earth's magnetic field breaking down and everyone going to die and bad things happening, is that Earth's magnetic field really does protect us from this radiation from the sun. Okay, so another kind of cool phenomenon is that magnetic forces will form between two current-carrying wires. So we said before that if you have current in a wire, it'll create a magnetic field around it. And likewise, if you have a current in a wire that's in a magnetic field, there'll be a force pushing or pulling it up or down or left or right. So if you have two wires and both of them are carrying current, the first wire will create a magnetic field, and that magnetic field will put a force on the second wire, pushing it or pulling it. Then the second wire will create its own magnetic field, and that will put a force on the first wire, pushing it or pulling it. And the net effect of that is either the two wires get pulled together or they get pushed apart, depending on the direction of the currents. So the two wires create magnetic fields that put forces on each other, and so we can calculate the magnetic field created by the first wire and then the effect of the force on the second wire. So this is pretty exciting. Here's a nice picture to kind of illustrate what's happening. The first wire will create a magnetic field over here, and this magnetic field coupled with this current will cause a force. So if both of the currents end up pointing the same direction, left or right, doesn't matter, the two forces will be towards each other and they'll attract. If the two wires have currents in opposite directions, one's going this way, one's going this way, because of the orientation is opposite, the direction of the forces will all be opposite, and they'll repel each other. In both cases, the formula is the same, it's just one is attractive, one is repulsive. And I encourage you to go through the math to get this, or ask in class, and I'll show you how we can derive this formula based on the formula for the magnetic field created around a current carrying wire, coupled with the force on a wire in a magnetic field. Anyway, the force is the mu naught value times the length of these two wires, times the current in the first one, times the current in the second one, divided by 2 pi times, you could use d or r, which is the distance between them, or the radius from here to here. Sample problem. Where should I place wire B so that the net force on it is 0? So it's kind of exciting. It's similar to the problems we had in the math section. So this would be a math, just a heads up, this would be a math problem. The concept is for everyone, but the math would just be for students taking this class in terms of math. Where should I place wire B so that the net force is 0? That means that whatever force is attracting it this way is also equal and opposite force attracting it this way. So the force, or the wire, has a current out of the page in all three cases. So if we go back and look, that means both of them are in the same direction, so they're going to be attractive. So this guy is going to have a force this way because it's attracted here, and it's also going to have a force this way because it's attracted by wire C. So these two forces are going to have to be equal and opposite. Now, the length of all the wires is going to be the same, so mu naught is going to be the same. So we have I1, I2, 2 pi is the same in all cases, and then d. So we have mu naught IA IB L over 2 pi times this distance, d. That's the force between these two guys. That has to equal mu naught IC IB times L over 2 pi times this distance. And if the total here is 2 meters, and this is d, then this is 2 minus d. Okay, so mu naught is in both, so that cancels out. 2 pi is in both, so that cancels out. L is in both, so that cancels out. And the current B is in both, so that cancels out. So a whole bunch of stuff canceled out, and we're left with just current in A, which was 5 amps, over D. So I'm going to kind of go up here now. So 5 amps over D equals IC is 15 amps over 2 minus D. And to solve this, we can cross multiply and divide. If I cross multiply here, I get 10 minus 5D equals 15D, cross multiply. Add 5D. So we get 10 equals 20D. So D equals 10 over 20, which is 1/2 of a meter. So the distance is here 1/2 a meter, and on this side 3/2 of a meter. So because this charge is 3 times higher, the distance is 3 times farther away, because it's inversely proportional. The farther away it is, the less force, but it's made up for that because it's a larger current. Okay, we're almost to the end. We can apply this idea that current through a wire in a magnetic field will have a force on it, and we can actually use it to cause things to move in predictable ways. And in fact, this is the kind of synthesis of the electric motor, which, as I'm sure you would all agree, is really, really helpful and important. So if you have a loop of wire, it's a combination of 4 segments of wire, all inside of a magnetic field. Each of these 4 segments of wire, using the right-hand rule and the formula F equals I L B sine theta, each of these 4 lengths of wire is going to have a force acting on it that's going to push or pull it. So without spending too much time to go through the details, the net force on these 2 sides will be outward, back and front. The force on the top and the bottom will be down and up. So at first you might think, well, that's kind of stupid. The net force is going to be 0, so nothing's going to happen. If you have a force forward and backward and up and down, they're all going to cancel each other out. And that's true. the net force is 0. So this entire loop is not going to translate or move side to side, but it will possibly rotate. So if the loop is oriented completely vertically, you'll have a force in and out, canceling it out, and you'll have a force up and down, canceling out, and there will be no net force, because you'll have a force here and here. It'll maybe try to stretch the loop out, but if it's a rigid material, the loop won't be able to get broken. However, if you have your loop oriented sideways, the direction of the force on this side will be up, and the direction of the force on this side will be down, and that will tend to cause the loop to rotate. Okay? And because once it starts rotating, it's gained momentum, it'll swing past and it will end up in this orientation again. And then the forces, since the loop is flipped over, the forces will reverse and it can oscillate back to here. So if you just had current going through it continuously, this loop might start to oscillate back and forth like this. And then you can use that to control things. But maybe you want something to continuously spin around, like say you want to attach this to the axle of your car and it will drive your car forward. What you need is that every time this rotates half of a loop, you change the direction of the current, so that even though this is flipped over, the current also flipped over, and so the two flips together make it keep going the same direction. And you can achieve that by what's called a commutator. So the commutator switches the direction of the electrical current every half of a rotation, so that the torque is always rotating it the same direction continuously. And if you put this coil of wire inside a permanent magnetic field with a commutator and a battery powering the current, when you turn the current on, it'll cause this to rotate, and then you can, using electrical energy, you can cause physical motion. So there are countless examples of this, but a simple one might just be a motor, or a hairdryer with a fan, or anything where you're trying to take electrical energy and cause something to rotate. That's essentially the definition of what an electrical motor is. The torque on the loop causes it to rotate, and we can use that rotation to run some kind of device. It requires the commutator to keep the orientation going the same, otherwise it would oscillate back and forth. But the electrical motor is the way to take electrical energy and convert it into mechanical energy via rotation. Okay, sample problem. I'm going to skip this one for now and leave it at that. So that's basically an overview of all the concepts. You've got permanent bar magnets that create magnetic fields around them, but you can't isolate the north and south poles. You've got current carrying wires creating magnetic fields around them. You've got coils of wire creating a uniform magnetic field inside. You've got the idea that not only does a current carrying wire create a magnetic field, but if you put a current carrying wire in an external other magnetic field, there will be a force on it. Additionally, if you shoot charges through magnetic fields, there will be forces on those. The direction of the force, you need to use a right-hand rule, which is a triad, which gives you that the force is perpendicular to the magnetic field and the velocity. And then there's applications in terms of wires attracting or repelling each other. And more importantly, and most importantly, the application of the electric motor, which has the net force of 0, but the net torque non-zero, which causes the loop to rotate, which can give rise to motion. We'll do a lot of more talk about these concepts and math in class, but this should give you a good introduction to the subject.